Please. All right. Hello, everyone. I'm Tyler Skluzacek, formerly at the University of Chicago, now at Oak Ridge, talking about scalable and distributed metadata extraction with Xtract. So I put my name on here, but obviously a ton of people in this room have also helped with everything in here. Scientists generate lots of data when they do science, right? And that is the key takeaway of the slide. That's a lightning talk. All right. So all of these giant data have information in them that people want to search over in order to navigate their data sets, right? Or to make them fair, but I prefer the term navigate. And so you have two options here. So here you might have like a picture of a dog. And so option one is to manually pull out everything. You might ask a person 20 questions. This is an image. This is a photograph. This has stuff in it. Option two is what I'm going to talk about today, is automated metadata extraction system. And so this is kind of, there's a whole bunch of these that are used in practice, but the idea is you have this centralized system that's thinking about where the data are, these compute resources as to where we can extract this metadata information automatically, and then also some sort of search interface. That was a slide I just took out to make this faster, but that you can use to search over these data, right? And so how do you extract metadata from files of very different types? So the focus here is science data. You have a repository. It's a collection of files. There's metadata that you can pull out from the files. And an extractor is, I'm just going to speak in technical terms, is something, it's like a Python function that has dependencies that you can use to just pull information out of a file. Input file, output metadata, right? And so I built this previously without funkex, but funkex, like if you think of these as fast functions, enabled me to do a lot of things. And so we developed a lot of extractors or funkex functions that do things. So you have some that are general to all science. You might have something that gets metadata about keywords or tabular files or C or Python, anything about that. Then you might also have domain-specific things such as battery data, materials data, spectroscopy, so on and so forth. And there's also like these principles for how we design extractors. I did just write and submit a paper about why I hate these principles. But if you want to read about them, see my thesis and then the follow-up paper about why I hate them. Okay. So I need to stop walking away from my computer because people at my defense told me I did that and I couldn't hear what I was saying. Okay, so if thinking about extractors as funkex functions, I kind of redesigned the model in kind of the last year since last time, where pretty much every extractor looks the same, but you put all of the domain-specific logic into a container, right? So this uses funkex as container workers. So pretty much what you do is you take any of these extractors that you're free to go look at to see how you actually input file output information. But it all runs through this. You have like these extract agents that are launched on the machine as part of the funkex function. It has these paths to where all the stuff they need is on the container. It executes all of the extractions as a batch, flushes all the metadata to disk, and then after the fact, it gets flushed somewhere else. So why is funkex important? Well, it enables us to have a flexible computing model. So if you want to extract all your data at the edge, at a center, or some combination of in between, whatever is fastest, whatever you want to do, whatever allocations you have, made possible by funkex and Globus, right? And so Xtract is a metadata extraction system for science that orchestrates the application of these extractors to science files to get information out of them. The important thing is users submit extractors, launch jobs, and monitor progress via the Xtract SDK. I put the GitHub link at the end. The crawler recursively scans over each file in the repository to make a big list of everything you possibly have. Extractors wrapped as funkex functions are invoked at the facilities. Funkex providers enable automatic scaling on these diverse machines, as we all know. Files can be moved between machines for more optimal processing by using Globus, and endpoints are all configured using a CLI I built to make my thesis look good in the end, but it actually made Xtract a lot better. So I'm glad I did that. So just in terms of performance graphs, I'm going to fly through these at 100 miles per hour. So like the extract here use case, say you want to move all of your data and process them, at a center. We show that Xtract is fairly quick at performing those extractions. Kevin asked a question during my thesis that was, why do these look like little blocks? It's because you can't just flood Globus with 100 million transfers. You just have to kind of wait until you have a ball big enough and then tell Globus to transfer the data. So we just see that this is pretty fast on 50,000 files. Extract there. So if we take the entire materials data facility, we can just run the whole thing on Theta and it scales fairly well. Up to 4,096 nodes, it scales, almost well at 4096, but really well at 2048. And then extract anywhere. So we show that there's some scheduling configuration that exists in which you can move things around between machines, and the goal is to get them all to finish at the same time. And so if we kind of go back to this slide, having funkex functions that enable us to, do things wherever we want enables us to have that more flexible, efficient compute. So you kind of are wondering like, okay, you extract all this metadata. Why is that useful to me whatsoever? Well, the fact is you can load it all into a search portal or some sort of like search index that's Jupyter accessible, which we did for a cool user study. And people seem to like it. That was the takeaway from that user study. And so I made a list of things I'm particularly excited about. First is the FuncX container service. So you can imagine that, you know, designing containers for extractors is a very tedious process and a lot of bash scripts, especially every time I make an update, then I have to do it all again. So it gets very, very tedious quickly. So I'm very excited about that. Someone mentioned service-owned endpoints, and that was something I would like to have as well, because these computing centers don't like people running things willy-nilly necessarily. And the Minnesota Vikings 2023 Super Bowl run, 2 out of 3 things on this slide are likely to happen. Okay. And so the last thing I'm excited about is we're transitioning Xtract from, you know, UChicago to ORNL at the moment. So it's soon to be again available for use. And so for future work, I want to design these little micro extractors that help us, you know, better share extraction logic between different extractors. So I don't like this big extractor library where multiple extractors do the same thing twice. Combine workflow and file metadata, because data usually aren't the result of, you know, they're not made in a vacuum. They're made as a context of this larger science process. And then this cool thing that Ryan Char told me to put in my thesis, which I really like a lot, which is AI enhanced storage to support ML applications. You probably don't even remember that, but it's a good idea. Best idea you've ever had. All right, so if you want to learn more, shoot me an email. Any questions? Yeah.
How do you think about the trade-offs of compute and storage? And like did you move all of MDF to Theta to do like the extraction? Was that like a good thing?
So we kind of set up all of the simulations, right? Because it all lived like pretty much at Theta. So I had a full copy of it just sitting at Theta. Mm-hmm. And so we kind of explored the different things. So for example, if you do something like this, for this experiment, we wanted to move all of the data from somewhere to MDF or Midway, but you had to move the whole thing. As you could see, we trimmed that down to 50,000 files because it was too ridiculous to move the 2.2 million files, right? Mm-hmm. And so obviously this plays into that trade-off of you would never want to actually do the whole movement unless there was something extreme, like maybe a 14-day wait on a queue, mm-hmm, or something like that.
Questions? We have last questions. Where was that swamp on the first slide?
Oh yes, I'll show you where I found this picture of a swamp. Google.com/images.
Did you add the lightning? Or was it there?
I did add the lightning for the lightning talk. That's a good question, Don. These are all great questions.
So you got a transparent background lightning that you can just throw on the top of things.
Yeah.
Kyle would like a copy of that.
I would like a copy.
I'm surprised more people didn't.
I mean, it was very similar to your thesis difference, just much faster speaking.
Yeah.
Thank you, Tyler. I don't know what to say about the Vikings.